Hey everybody, so welcome to our Calculus 1 Exam 2 review. So if you're joining me, just so you know, we are doing the recording live and in living color right now. And if you want to see this recording again, go into our online math resources. Scroll down here, click on Calculus with Analytic Geometry. Click on Test Review Materials. And right here, you will see Review version A. Now, just so you know, my partner in crime is also going to post 2 extra examples here for an extension of exercise 17 and an alternate question for number 18. And there is a video and a solution guide for that. It is not because of my partner in crime did something wrong. I think the questions that I had my partner ask, they weren't the right questions. They were the wrong questions, and I wanted to update those. So you'll probably see something that gets modified in here that says, hey, this is like an exercise 17 extension problem, where I take the same problem and ask you a different question to it. And then I'm going to have an alternate exercise 18 problem. But here is the blank review. Here is the solution guide that we are going to be working on right now. And then there will be a nice, lovely video, which we're recording right now. So this is where it's all located for exam 2 for calculus 1. With that being said, I'm going to jump on out of here because I've got the review already loaded for us. And I'm going to be using Desmos. And I will also talk to you about as we do this, because I know some professors have you submit questions for work. So I'm just going to say for my class, if you are one of my students, I'll tell you which questions I want you to submit work on. Other professors might be a little bit different, just to kind of let you know. So I need to open up my document camera. I forgot to do that. But here's our exam. My document camera is opening up. Here it comes. All right. So our first 2 questions I already have written down here. The cool thing is on your exam, these first 2 questions, I'm not having you submit, but what you are doing is you're giving me a rough sketch of what the derivative of this blue function is. And the cool thing is it's multiple choice. So let's actually do this as if we were going to submit something. Let's do this by hand and talk about it. So these are questions 1 and 2. Again, these are going to be multiple choice, but we're actually going to graph them by hand here. So when we're graphing derivatives by hand, and this is coming from like section 2.8, what are some things that you need to be aware of when you're looking at the graph of f of x? Oh, and there's only 18 questions on this review. What are some things we got to watch out for? What are things that are going to help us graph the derivative? They're kind of three items.
Max and minimums.
Yes. Let's look for max / minimums. Because if there are max and minimums, that means we have x-intercepts on the derivative. Okay, what else?
Corners.
So look where it's undefined. So like corners. What else will lead to an undefined derivative? Corners and
The x-intercepts.
nope. How about discontinuity? If my graph is not continuous, derivatives can have problems. What else?
Is it where the line is the steepest that it
Not,
almost looks?
I like where you're going, but what is the steepest kind of line that we can have for a derivative?
Vertical line?
Yes. Look for vertical tangents. And there is one other. And that is asymptotes,
Well, asymptotes.
vertical asymptotes, to really kind of be specific. So these all cause our derivative to have problems, to be undefined. All right, and then one other piece that we should be looking at to help us graph our derivative. What is that? The slopes.
Mm.
Are slopes positive
Let's
or
see.
negative? We got to know what our slopes are doing.
Okay.
You know. All right. So let's start with this. Let's start with max and mins. Do we have any max or mins for question 1?
Yes.
Yeah, we got 2 of them, right?
Yep.
We got a max right here. We got a min right here. So that means we have 2 x-intercepts. Also, kind of like since you were talking about, well, now we'll come back to that. Do I have any corners, discontinuities, vertical tangents, asymptotes on this guy?
No.
No. So our derivative is going to be entirely continuous because this function is entirely continuous.
Mhm.
What are some other features you notice where we might have maybe maxes and mins or horizontal asymptotes?
At the end, when it gets close
Yeah.
to the
Yeah,
x-axis.
right here at the end, it's almost kind of like it's going horizontal towards some
Mhm.
horizontal asymptote. So definitely at these ends, we're going to be close to this x-axis. Okay,
Yes.
perfect. All right. So let's talk some more then. Let's talk about these slopes and whether we're positive or negative. So as we move from left to right to our first x-intercept here, as we move along here, what kind of slopes do we have?
Well, going from left to right is starting to increase and then it decreases back down.
Okay, but let's talk, are my slopes going to be positive or negative? Between these two,
Oh,
are we going to be positive or negative?
positive.
And then I like what you were talking about because right here, we're not very steep. But then as we move along, we're getting steeper and steeper. And then we're going to reach our steepest somewhere here in the middle. And then all of a sudden now we're going to go back and we're going to start to get less steep until we're almost horizontal. So you said that these are positive. So we need to make kind of like a positive hump here. So it's going to kind of look something like that. All right, now what's happening between my 2 x-intercepts? So from here to here.
It's a negative slope.
Yeah, it is a negative slope.
Decreasing.
And right here, actually at the origin, that's where our slope should be the steepest negative, as you were talking about. Right here at the origin, that's our steepest negative. So it's down here somewhere. Right there for this guy. And then what's happening to these negative slopes as it progresses through here? How do they start? And how do we start to move? So what are my slopes doing here?
They're decreasing.
Well, no, careful. These are negative slopes,
Mm-hmm.
but what's happening here to here? What are my slopes doing? Think
So
steep.
from the max to the origin,
Yeah. Think in steepness. What are my slopes doing? My slopes are getting bigger negative. Because
yes,
remember, we said this is going to be the steepest slope. So they're going to start close to zero and then get bigger and bigger and bigger. And then what's going to happen after the origin?
they're gonna keep getting bigger on the negative side.
Until we get down here. And when what's going to happen here?
It's gonna start increasing, but on the negative side.
No, it's going to start going back to zero, silly. We're steep, we're steep, we're less steep, less steep. So between there, does something like that.
Yes.
It's close to zero here. And we start increasing that slope, increasing. Here's the steepest. And then all of a sudden we start decreasing. We're going back towards zero. All right. So what's going to happen over here on this side? From my x-intercept on off to positive infinity. What's going to happen in here?
It's gonna be like the first part is going to
Exactly.
go back up and then approach
That's right. We're going to be
x-axis.
not very steep. And then we're going to get bigger. And then we're going to hit our max. And then all of a sudden now we're going to start to shrink back towards zero onto infinity. So it's going to look a lot like the first side. So we want something that looks like that. Again, our sketch is rough. They have a better sketching tool. So if we go back and we look, which
A.
picture is it?
A.
A. And if you look at the other pictures and analyze it, this doesn't make sense because all they did was just reflect this over the x-axis. That's not what's going on. This one kind of makes sense. We got two x-intercepts, but it's our graph that we just drew upside down. We're not up here on the positive side. This big hoop should be down on the negative side, like A. And then this guy only has one x-intercept, so you can throw that one out right away. So you can actually kind of look at these and be like, oh, this is only, also this one only has one x-intercept, so you throw it out. These two are junk. So you had a 50-50 shot if you think just in terms of x-intercepts. All right, let's do number 2. And let's walk through its graph. All right, so what are some things that we could talk about here? Do we have max and mins?
Yes.
Yes. We have what?
Well, you have a min at the end of the curve.
Right.
You have a max at the corner.
But what can you tell me about this then? I know it's a max,
Right.
but you also just said a key word. It's a corner.
Right.
So what do you think is going to happen there at my derivative?
It's going to be undefined.
It's going to be undefined. And with my graph, we'll have open circles here.
Yes.
Okay. So we know that we definitely have one of these going on. We got that corner. We know that we got an x-intercept. So now all we got to do is talk about slopes. Okay. So what's happening on this side of my graph? From here to the minimum or to our x-intercept. What's happening here? What's happening to the slopes and what are they?
So the slopes are going down.
Okay, so they positive or negative?
They're going down, but they're positive.
No, these are not positive slopes. Draw one in. These tangent lines are what? That's a negative line.
So what do you mean when you say negative or positive slopes? Like what direction they're going?
So yeah, so tangent lines that increase from left to right, that's a positive slope.
Right.
Tangent lines that decrease from left to right is a negative slope. You need to know that because that tells you whether you're going to be up above the x-axis or down below the x-axis.
Yes. So that's a negative slope.
So these are all negative. And then what are they doing? What's going on with their steepness?
Well, they're their steepest at the top, but then
Uh-huh.
they get less and less steep and
Okay.
go towards the minimum.
So we're steepest at the top, which means we're really negative, and then we're coming back towards 0.
Yeah.
Okay. Now what's happening after my minimum to this part of this continent? Well, to this part where my derivative is undefined. What's happening between here and somewhere right in here? What's
Okay.
going on?
So you have a positive slope
Yes.
that is going towards that undefined point.
Going towards that undefined point, and they're getting steeper and steeper and steeper, right?
Yes.
Well, this is a horrible graph. Let me redraw this a little better because I'm running out of room.
Minus.
Speed up the drawing process. All right. I'll be a little bit better this time. Just made it too steep.
Oh.
Okay.
There we go.
So we're really steep, and then
Yes.
we become positive, and then we're right here. What's going to go at the end of my line right here?
An open circle.
An open circle. All right, now let's talk about this. What
Yes.
is this figure? What is that right there?
A negative line.
That is a negative line. What do you know about the derivatives of lines?
That the derivative of the line is the same thing as is the line.
Well, it's the
Well,
same as the slope,
yes.
which means that the derivative of a line is a constant number.
Yes.
It's a horizontal number. So I like what you said. What kind of line was this again?
A negative line.
A negative line. So that means the slope of this line is
A negative slope.
a negative slope. So we're going to draw an open circle down here, and then we're just going to draw a horizontal line because that slope will always be constant there. It's not going to change. And that is what f prime of x looks like. So if we go back and we want to find what our picture is, which one is it?
D.
It is D.
As in there.
D is the picture that looks like ours. All right, moving on. All right, number 3. So we got this graph from the US Department of Energy, and it shows how driving speed affects gas mileage. So you got this fuel economy. F is measured in miles per gallon. We've got speed is measured in miles per hour. And then we got 2 questions down here, 1 multiple choice and 1 fill in the blank. So we got fuel economy, and it's measured in miles per gallon. I always like to put this down there. And we got that speed, V, is measured in miles per hour. All right, so the first things first, they want us to know what is the meaning of the derivative. So what does f prime of V mean? Well, let's talk about this. So they gave us prime notation. Sometimes it's better to write this in Leibniz notation.
Mhm.
So if I write this in Leibniz notation, what would that look like? D of what over D of what?
D velocity. So V. D over dV. Oh, D.
Oh, okay. You said D over dV,
Yes.
and that would be our operator, but in Leibniz notation, it'd be dF over dV.
Okay.
Okay, we're going to talk about the change in fuel economy over the change in speed. So looking at our choices then, which one of these is the meaning, thinking about it from the dF dV standpoint?
Oh, okay. So A.
It is not A.
Oh, C.
It is C. Excuse me.
Mm-hmm.
So if I come back to this, just to talk that through. So this is the one, this is the prime notation. So this is your dependent. This is your independent. F depends on V. So our instant rate of change, IROC, instant rate of change of fuel economy, that's our top guy, with respect to V, our bottom guy, the speed. So C is our answer because this is the derivative of instantaneous rate of change of the fuel economy with respect to speed. Part B, and I always like to ask this question because I always like to think about this. What are the units about on F prime? What would the label of this be?
Hmm.
What do you think? What would the units be?
would it be gallons per hour over miles?
So let's take a look because this one's tough to think about. So if it's fuel economy on top, that's miles over gallons. And we're going to divide that by our speed,
Mm-hmm.
which is miles per hour. But we don't divide fractions. What do we do?
You multiply and flip.
You got it. Keep the top, change division to multiplication, and then flip the bottom.
Mm.
What is going to happen?
Yeah, the miles are gonna cancel out, and you get um the hours per gallon.
Hours per gallon. Okay. We get hours per gallon. So we want to know for part B, kind of thinking about that, what speed should you drive if you want to save on gas? So what do you think we're asking about here in part B? What are you looking for graphically?
The I want to say the minimum.
Not really, because that graph doesn't have a minimum. Think this is all about derivatives. So what kind of derivative do you think you'd be looking for?
Hmm.
You're looking when it's horizontal. Because if you think about it,
When you graph the derivative.
when you graph the derivative and it's horizontal, because our derivative is in hours per gallon. Well, wouldn't you save a lot of gas if you were at 0 hours per gallon?
Yes.
So where is it that the derivative is going to be 0? Horizontal. What is the miles per hour? What do you think? In this case, you're looking for a maximum. A maximum on the graph, and there is one.
50.
50. 50 miles per hour. And there you go. All right, number 4. For my class, this is one of those turn-in problems because I want to make sure that you are not using shortcuts. So I want you to find the derivative of f of x equal to 2 plus 4x minus 8x squared. And I want you using the limit definition from section 2.8. So no shortcuts.
All right.
So what is our limit definition? Do you remember?
Yeah. So the derivative is limit as h approaches 0,
Good.
it'll be 2 plus.
Don't plug in just yet. Just give me the
Oh,
formula.
okay. So as h approaches 0, it'll be x plus h,
F of x plus
f
h.
of x plus h minus f of x over h.
All right. Now we'll start plugging in, and notice we're going to keep the limit as we keep going, unless we do some side work, and I will do some side work. So what does it look like when we just plug in?
Right. So it'll be 2 plus 4 times x plus h minus 8 times x plus h squared minus,
And you'll want a parenthesis after that because we
right.
are subtracting the entire function.
I was going to change the signs, but okay. So
Oh, it's okay.
so minus 2 plus 4x minus 8x squared all over h.
All right. So I'm going to go ahead and do some side work first and
Yes.
take care of all the h information. So I'm going to work with the 2 that you have given me plus the 4x plus h minus the 8x plus h squared. So a little bit of side work. So I don't have to keep writing limit over and over again. So I'm going to take care of the square part. And we all know that if you take x plus h and square it, because we've worked with this so much,
Yes.
that you get the following. You get x squared plus 2xh
Plus
plus
h.
h squared. So that's what happens when we FOIL out x plus h times x plus h. And then now there's just a quick little distributing. 2 plus 4x plus 4h minus 8x squared minus 16xh minus 8h squared. So that takes care of my h piece. And I'm going to go ahead and now return back to my limit and use that information. So the limit as h goes to 0 of 2 plus 4x plus 4h minus 8x squared minus 16xh minus 8h squared. And then now talk to me about these signs you wanted to change earlier. What do we got left here?
Yeah, so it'll be minus 2 minus 4x plus 8x squared
All right. And all this is
over
over
h.
h, which there's some simplifying there. What's going away?
The 2's are going away.
Yep.
The 4x is going away and the 8x squared.
Yep. Anybody without an h, you're gone.
Right.
So we have 4h minus 16xh minus 8h squared all over h. Now what happens?
So now you can factor out an h.
So the limit as h goes to 0 of h parenthesis, said factor out an h, so that would give me 4 minus 16x minus 8h all over h. Now what?
Oh, the computer just. All right, I'm back. Okay. Yes, so the h's are going to cancel out.
Yep. So that'll leave us with 4 minus 16x minus 8h. And direct substitution leaves us with what?
4 minus 16x.
Absolutely. And there's the derivative. And there we go. No shortcuts. But if we do check with shortcuts, look at this. That'll be 4. And then bring the 2 down and multiply the 8. So that's negative 16. Subtract 1. That's x. So it matches. Yay. All right. That's the only limit problem you have on this.
Nice.
Okay. Number 5. So number 5, I want to know, where is f not differentiable? Where are we going to have those problems? And we talked about that earlier. Where are the problem areas on graphs? What do we look for?
Yes, the corners
Corners. What
and
else?
where the points are undefined.
Okay.
Asymptote.
So discontinuity.
Yes, asymptotes. And well, vertical lines. So vertical asymptotes.
Vertical tangents.
Vertical tangent.
Okay. So where do we have the problems?
So you okay, dx. So dx equals -4.
Because that's a corner.
Yes.
So then you'll put a comma. Where else?
Yes. X equals 0.
Because we have discontinuity.
X equals 2 because of the vertical tangent.
Yes.
And
And that's it.
yeah, that's it.
There you go.
Oh, not bad.
So -4, comma 0, comma 2.
Yes.
Moving on. So here you're going to differentiate for me. We got s of t equal to 1 over t plus 1 over t cubed. So now we have lots of rules. So you could do the quotient rule on this twice and then add those two derivatives together. But there's an easier way.
Yes.
What can we do to make this a little bit easier for us?
You can make both powers.
Yes, let's use that power rule. So what is 1 over t really as a power?
T to the -1.
Yepers. Plus, what is 1 over t cubed?
T to the -3.
Perfect. Yeah, it's much easier to think about this as a power and just do the power rule than trying to do the quotient rule with this. That would just be crazy. But do not get me wrong, the quotient rule will end up at the same answer, but the power rule just so much faster. All right. So what is the derivative then of t to the -1?
Yes. So -1t to the -2.
Okay. Plus, what is the derivative of t to the -3?
-3t to the -4.
Okay. So if we kind of clean this up, it looks like this. -1 all over t squared. And then I'm gonna go ahead and bring that minus out in front because plus a negative is a minus. And then
Mhm.
this is 3 over t to the fourth. And that's the answer that they're really looking for. Now, just so you know, I mean, you could take this because we are smart mathematicians and we could make this one fraction. There will come a time where you will want to put this together and make it one fraction. We're just not there yet. But if you did make it one fraction, the common denominator would be t to the fourth, and you would end up with negative t squared minus 3 on top. So that is one way to kind of simplify that down and combine it into one. But this answer is a-okay. Okay. Most of what happens with the simplification in our web assign is most of the time the simplification is simply pulling out a GCF. So when you're thinking about simplifying, look for GCFs. Obviously, there is no GCF in this one. And this answer, I know for a fact, is really what they have. All right, number 7. Number 7, another differentiation. This time we got g of x equal to 1 over the square root of x plus the cube root of x. This one is a lot like what we just did a moment ago. We can use the quotient rule, but there's an easier way to do this. How else can we write g of x?
You can write it as powers.
Powers, absolutely. This is just a power rule in disguise. So
Yes.
what does 1 over the square root of x look like?
X to the negative a half.
Okay. Plus, what does the cube root of x look like?
X to the 1/3.
Okay. So moving on, we want the derivative. So what is the derivative of x to the negative 1/2, which we have dealt with a ton?
Yes. So it'll be negative a half x, and then let's say negative a half minus 1. Negative 3/2.
Yep,
3/2.
negative 3/2. Plus, what is the derivative of x to the third?
So 1/3 x to the 1/3 minus 1. Negative 2/3.
Okay. So the book, what they will do, and this is the answer. I'll put the -1 on top, and all they're going to do is just shift that to the bottom. And they actually left it as exponents, which surprised me. They left that one as that. And then plus 1 over 3 x to the 2/3. This is how they left that answer. I kind of took it just one step further, just so you know, and I always took it out of those fractional exponents. So if you put it back into radical form, it looks like this. -1 over 2 square root of x to the third plus 1 over 3 cube root of x squared. I would have thought the book would have done this, but they didn't. But they actually just left it with the exponents as positives.
Yes.
So there you go. They're keeping the simplification really easy for us. And that's all right. Because there was a lot, I mean, we could have probably rationalized this and gotten common denominators, put it all together as one, but we don't need to do that. All right, number 8, f of x equals e to the x minus x cubed. Now, if you look on this one, we're looking for two things this time. We're looking for f prime and f double prime.
Yes.
So we want f prime of x, and then we'll do f double prime of x. So again, this one is just nice and easy. We'll do a power rule, and you got an exponent or an exponential that you got to take the derivative of. So let's do this. What is the derivative of e to the x?
Yes. So the derivative of the x is e to the x
Minus,
3x squared.
there's our first derivative.
Mm-hmm.
Now, if we want f double prime, all we're going to do is take f prime and take the derivative of it. So again, what's the derivative of e to the x?
Yes. E to the x minus 6x.
Perfect. And there you go. Derivative of e to the x is always e to the x. And this was just the power rule in action. Number 9. So number 9, they're giving us this particle. And I'm going to call that s of t and not just s, where s of t is equal to t to the third minus 27t. So we got this equation of the motion of a particle where s of t is equal to t to the third minus 27t. We know that s is in meters, t is in seconds. And we're going to assume that t is greater than or equal to 0. That's important for us because that means we're not time traveling. Okay. Again, though, if you invent time traveling, let me know. I will be a silent partner and we will be filthy rich. So time starts at 0 seconds and moves on from there. So number 9 is a lot like number 8. Okay. Even though it doesn't seem like it is. The first thing they want us to find is the velocity of t. Well, that's just really doing what?
Finding the derivative.
Finding the derivative of s of t. Perfect. All right. So what is the derivative of s of t?
3t squared minus 27.
Perfect. And again, I always like to talk about this. What are the units?
Meters per second.
Good. Meters per second. Even though it didn't ask us about that, I always like to ask. So I want to make sure that we know what we're looking at. Part B, they want acceleration. What is acceleration then? How do we find it?
Double prime.
Yeah, it's really the derivative of the velocity. So take the derivative of velocity.
Eh, 6t.
Perfect. What is the units for the acceleration?
Meters per second squared.
You got it. Meters per second, or per second squared. Perfect. Halfway through now. Halfway through. All right, number 10. We want you to find the points on the curve y equals x cubed plus 3x squared minus 9x plus 2, where the tangent is horizontal. It says write them as ordered pairs and use commas to separate. No graphs. So we want this pure algebra style. Okay.
Okay.
Got this written down. Here we go. So if we're looking for horizontal tangents, algebraically, what am I asking you to look for? Because we're not going to look at a graph. I'm not going to graph this.
I mean, you can't set it equal to 0 because that'll get you vertical lines.
Set who equal to 0?
I mean, you would set x equal to 0. I mean, no.
It does have something to do with equal to 0. We want to look at something set equal to 0.
I mean, find the derivative and then set it equal to 0.
Yes. You want to look at the derivative set equal to 0 and find all those x-intercepts. That's what a horizontal tangent is. Remember, those are the x-intercepts of the derivative. So if we know what the derivative is, we can set it equal to 0 and solve for x. So what is y prime going to be?
3x squared plus 6x minus 9.
Perfect. So there's our derivative. Now all we have to do is take this 3x squared plus 6x minus 9, set it equal to 0, and solve. How do we solve this? What are we going to do?
You can pull out a GCF first.
Okay, so let's do that. That's going to make things easier. So we pull that GCF of 3 out.
Yes.
Leaves us with x squared plus 2x minus 3. Now what?
Yes. So then you do. So when you factor, you should get.
Good. We're going to factor it. Yeah.
X plus.
Or you could run the quadratic formula if it doesn't factor.
Oh, it does.
It does. I know it does.
Yeah. So.
Oh, come on. You got this.
Yeah. I don't know why. Yeah. So x plus. Oh, that's yeah. X plus,
X,
and then x minus 1.
Oh, wait, yes. X plus 3, x minus 1. Sorry. I was
Okay.
thinking backwards. There it is. So if I want to know what x equals, I'm just going to take all this and set it equal to 0. So we got 3 equal to 0, but
Oops.
so I'm so sorry about that. I somehow got disconnected. So we just factored. And then we're going to take each one of these factors and set them equal to 0. So 3 equal to 0, that doesn't make any sense. That's just nonsense. But x plus 3 equal to 0, that means we now know that one of our horizontal tangents, our x-intercept for derivative, is at -3. And then x minus 1 equal to 0. So we have another horizontal tangent at x equal to 1. But remember, our question says we want ordered pairs. So we need to take these two answers and we're going to plug them back into the original to figure out what the ordered pair is. What is the point? So we got 10, y equals x cubed plus 3x squared minus 9x plus 2. So we want to figure out what is y of -3 and what is y of 1, not -1, Mr. Armstrong, +1. So all we're going to do is plug in and we're going to get our 2 points. So we got -3 cubed plus 3 times -3 squared minus 9 times -3 plus 2. So what does that give us?
I got 29. I'm of the negative.
29?
Yes.
Absolutely. Because this gives you a negative 27. This gives you a positive 27. They cancel out. This will give you a positive 27 plus 2 is 29. And then plugging in 1. We get
-3.
-3. Because I get 1 plus 3, which is 4, minus 9, which is -5, plus 2, -3. So our 2 points are -329 and 1 comma -3. That's what they're after. Number 11. And for my class, number 10 is a problem that you will turn into me. Number 10 is one of my turn-ins. All right, number 11 and 12 are pretty similar to each other. Number 11, it's given us some information. We know that f of 5 is equal to 1. We know that the derivative of f of 5 is equal to 3. We know that g of 5 is equal to -9. And g prime of 5 is equal to 7. We have 2 problems here. We want to talk about what is f times g, the derivative of that at 5. And then part B, you're going to do f divided by g, the derivative, evaluated at 5. Well, A is just practicing the product rule. What is the product rule?
Hold on, give me a second. Yes. So the derivative. Oh my God. Derivative of of
The first, which
the
is
first
f,
times g plus the f times derivative of g.
good. And so the cool thing is we know all these answers. What is f prime of 5?
3.
Times what is g of 5?
-9.
Plus what is f of 5?
1.
Times what is g of 5?
7.
All right.
3 times 9 plus 1.
-20,
-20.
you said?
Yes.
Yes, I agree. Because this is just 7. So that gives us -20. That's it. There you go. There's part A. And then part B, they're testing the quotient rule. What is the quotient rule?
Whew. Yes. So I mean I do g times f prime
So the low times the top derivative.
minus g prime times f
So the low derivative times the top.
over g squared.
Okay. And there it is. There's our formula. All we got to do is plug in. So what is g of 5?
G of -9.
Okay. What is F prime
3
minus, what
7
is G? Okay. F,
times 1
what is our G again?
negative 9 squared.
Okay. Well, we kind of already know the top.
Yes.
I mean, we know that this is negative 27 minus 7. That should be negative 34 all over
81.
81. Question is, does that reduce any?
No.
Then that is our answer. Okay, number 12 is a lot like that, except we're going to be just a little bit more general. So in part A, we've got y equals x cubed times f of x. And then in part B, we've got y equals f of x all over x to the 8th. Again, all we want to do is differentiate. And the cool thing is these are multiple choice, so no worries there. All right. So how do I get y prime?
So you do the product rule.
So derivative of the first times the second plus derivative of the second times the first.
Yes.
So what is the derivative of f of x?
It would just be the derivative of f of x.
You got it. Because our directions did say that the function f is differentiable. If it wasn't, then we really couldn't get away with what we're doing. And then we got the second function, which is what?
Yes. It'll be x cubed
Okay. Plus derivative of the second
3x squared
times the first.
f of x.
All right. And so that's what they're looking for. They didn't pull out a GCF, which they could have. So which one of these answers matches that?
D.
You got it. Okay. Part B. So this is just the quotient rule again. So going with what you told me, it is I always talk about high D-ho, so highs and lows. So this
Yes.
is the high, this is the low. So it is ho D high, so my low times derivative of the top minus high D ho, the top, times derivative of the bottom, all over ho squared. That's how I like it. I think it's caught on for me quite a lot. So let's plug in.
Yes.
Derivative of, or sorry, the bottom.
X to the 8 times
Derivative of the top.
f prime of x minus
Minus top
f of x,
Derivative of the bottom,
8x to the 7,
all over bottom squared.
x to the 16.
Okay. Now on this one, they did do some cleanup. So what can we do with the numerator up here?
You can factor out an x. Whoa.
Yes.
No.
Factor out how many x's?
Yeah, you
X
can
to the what?
7.
To the 7. And that will leave us with x, f prime of x minus 8 f of x all over x to the 16th. And now what can happen?
Now the exponents are gonna subtract each other.
Yeah. These two are going to start canceling out and go into war.
Yes.
And so what's left in the numerator?
Would it be um so x f prime of x minus 8 f of x.
What's in the denominator?
X to the 9.
Okay, that's what they're looking for. So there was a little bit of simplifying on there. So the question is, which one of those is our answer?
Oh, sorry.
Oh,
Wait.
she doesn't have it up there. I think she was going with, it should have been B.
Yeah.
So it should have been B. That should have been a minus there. Because everyone else is too far off. It should have been B. So B is the answer. I have to go back and tell my partner in crime to put a minus in that one. But B is the answer, even though that should be a minus in there. All right. From 13 on, these are where, for my students and a couple other professors I know, you're going to be submitting work. So 13, 14, 15, 16, 17, 18, you're submitting work to me. All right. So number 13, I think if there's going to be a problem that students might have on this exam, this is going to be the one, because there is so much that goes on in this one. And there are many ways to tackle 13. Okay. So number 13, we've got this, and we want to differentiate. That's it. So we've got e to the 3 theta times tangent 4 theta minus the square root, or 2 minus 2 square roots of theta. Talk to me about some things that you see here. What kind of differentiation are we going to be doing in here? What kind of rules are we going to be following?
Well, you have the exponential rule.
Mm-hmm. So we got an e exponent. What else do we got?
I want to say chain rule.
We do got some chain rule with this e exponential. Also with the tangent, you have a chain rule going on.
Yeah.
What else? Got a power rule.
Right.
And what's going on between these two?
Oh, I was gonna ask if you can ln both sides
Um,
and cancel out the e.
that's a good question, but no, we don't want to do that.
Okay.
We don't want to do that.
Yeah.
but I like what you're thinking.
Well, they're multiplying each other, so product rule.
Absolutely. And now, I have had students ask, can I just distribute that through? You can, but that just means that you're going to be doing the product rule twice then.
Mm-hmm.
It's going to become even more messy. Do not get me wrong, you can do that. But I would just leave it as this and have a product rule for this whole thing. Because remember, the product rule is derivative of the first times the second plus derivative of the second times the first. And that's how I would approach this problem.
Mm-hmm.
And I'm going to go ahead and kind of take, and I forget that they use G in the front, so I don't want to confuse you with that G. So let's call these H's. So what I want to do is I want to figure out what the derivatives of each one of these are, and then we'll just do like a plug and chug. So if f of x is equal to e to the 3 theta, and we'll let h of x, as not to confuse it with g, be the entire tangent 4 theta minus 2. And I'm going to call that theta to the 1/2. I'm going to go ahead and change it to its power. All right, so let's talk about this one. So the derivative of that first function is a chain rule with an exponent. So what is, well, remember with the chain rule, I shouldn't say what is. With the chain rule, you're going to take the derivative of the outside, which is the e part, times the derivative of the inside. So what is the derivative of e to the 3 theta, the outside?
It would just be e to the 3 theta.
All right, now we're going to multiply this by the inside derivative. What is the derivative of 3 theta?
3
3. So what we have here is 3
e to the
e to the 3 theta. All right, so now over here, let's talk about the derivative of this thing. So again, this is the tangent rule.
yes.
What is the derivative of the outside, which is the tangent? And then we're going to multiply that by the derivative of the inside, which is 4 theta. So what is the derivative of tangent?
Be secant squared 4 theta times 4.
You got it. So there's the first part.
Yeah.
Derivative of tangent is secant squared 4 theta. Derivative of the inside is just 4.
Yes.
Minus what happens over here.
Yes. So you bring the half. So it'll be theta to the negative a half.
All right. So again, just kind of rewriting. This is 4 secant squared 4 theta. Just move the 4 in front. I'm going to go ahead and write this the way it is. 1 over square root of theta. Okay. All we got to do now is plug in the pieces that we know.
Okay.
So now it's just a plug and chug. Instead of trying to deal with this thing as a whole, it's a little bit easier to kind of separate it out. And then all we do now is plug in, like what we did back on number 11.
Mm-hmm.
So what is f prime? 3e to the 3 theta.
Yes.
And we're going to multiply that by my h. Well, that is tangent 4 theta minus, and I'm going to go ahead and put that back into its square root. 2 square roots of theta. So there's the first part. we're gonna add that with what is the derivative of h? Well, we got it right there.
Yeah, the 4 secant squared for theta
Minus
minus
1 over square root of theta. And then times the first. E to the 3 theta. Now, the only cleanup that I kind of expect in this, because this is nasty looking. What do you notice both of these have?
hold on. E3 to the theta.
What do both of these have?
both?
Huh?
Can you point again which both do you mean? Oh,
So
well,
this guy and that guy, what do both of those have?
yeah, I see it. The e to the 3 theta.
So just pull that out. And then write down everything that's left. So a simple GCF of e to the 3 theta. So when I pull the e to the 3 theta out of the first one, I'm going to take this 3 and distribute it through as well, because this 3 is in front, but I'm just pulling out the e 3 theta. So that'll be 3 tangent 4 theta minus 6 square root of theta plus 4 secant squared 4 theta minus 1 over the square root of theta. That's the answer.
Beautiful.
Don't do anything else, even though I'm sure we could all get these to be a common denominator and put them all together. We don't have to go that far. Just pull out that simple GCF. There we go. 14. I think this is like, if there's going to be a problem on this exam, I think 13 is going to be the one that trips people up because there's just so much going on. You've got trig derivatives. You've got, oh gosh,
Chain
yeah,
product.
chain rules, product, power rule, exponentials. You got it all.
Yeah.
All right, number 14. This is implicit derivatives.
Yes.
So we got this x squared minus 7 xy plus y squared equal to 7. And we want to know what is dy dx. So who are we taking this derivative with respect to?
You're taking the derivative of y with respect to x.
There we go. Everything's about x. So our operator is d dx. We're going to take the derivative of x squared. And then I'm going to pull out the constant for the next one. And we're going to take the derivative of d dx of a product rule of xy. And then we're going to add on the d dx of a y squared. And remember, that's like the chain rule that's going on there. Equal to d dx of a constant 7. So this is what my derivative, all the derivatives that we're going to be taking. Now, remember when it comes to y, truly when you're dealing with y and taking the derivative of it, it's like the chain rule. Okay. But kind of in class, we kind of realized that really the trick is really you're going to take, it's like you're going to treat it like you're going to take the derivative of it and then just slap on y prime on the end.
Yes.
All right. So what is the derivative of x squared?
2x.
Minus 7. And then we've got a product rule in here.
Yes.
So we got the derivative of the first, which is x. So what is that?
The derivative would just be 1.
1 times times the second. So that would just be y.
Y.
Plus derivative of the second. So what would the derivative of y be?
Y prime.
Y prime times the first.
X.
So there's our product rule.
Mhm.
Plus, what is the derivative of y squared going to be?
We have 2y times the y prime.
There you go. Because the derivative of the power, the 2 comes in front, subtract 1. So that's 2y. And then you have to have the derivative of y. Equal to, what's the derivative of a constant?
0.
All right. So what do we do now?
Okay. So now you want to clean up the middle.
Okay.
So you can yeah, so it'll be 2x minus 7y minus 7x y prime plus 2y y prime
Okay.
equals 0.
Now what?
Yes. So now you want to move the basically the variables that don't have the prime to the other side.
Okay. So how do I move a positive 2x?
Yeah, minus 2x
How do I move a minus 7y?
plus 2 plus 7y.
All right. So what we have then is negative 7x y prime plus 2y y prime equal to 7y minus 2x.
Yes.
Okay. Now what are we going to do?
Yes. Now you can factor out a y prime.
Okay. Factor out a y prime. And I like to have a positive number first. So I'm going to put 2y in front and then the minus 7x behind that. And that is equal to 7y minus 2x. So now you're ready to tell me what y prime is.
Yes. So it'll be y prime equals negative 2x plus 7y over 2y minus 7x.
And there you go. Now, if there are GCFs that can be pulled out of these, I expect you to do that. Expect you to simplify as far down, but there's nothing that we can do. There are no GCFs that we can pull out. 15, we're getting there. All right, 15. Again, you're going to be turning this one into me. So the directions say use, well, we got this S of t equal to 4 plus 1/5 sine of 4 pi t, where S is measured in centimeters and t is in seconds. So the first thing they want you to do is to graph this. Okay. So all I'm going to do is go to Desmos. And then once I have my graph, I'm just going to take a screenshot of it. Okay. So I got to Desmos. I'm going to put f of x. I know they're t's, but I'm in Desmos, so I can use x. And I've got 4 plus 1/5. You are not expected to graph this by hand. Times 4 to get pi in there, put pi t.
So on the test, when we submit this question, we on the work submission, we send it as a screenshot. Okay.
Oh, shoot. No wonder it's not graphing. I put a T in. It should be an X. There it is. And so in here, I would like your graph to be from 0 to 10, and that will be in the directions. So I'm going to make my x-axis, and how I got to this, I clicked on the wrench, make my x-axis start at -1, maybe go out to 11 so I can see the 10. And I'm just going to kind of clean up my y-axis. I'm going to do a little bit of zooming in. So I'm going to come down here. Maybe we go to -1, and we'll go all the way up to 6. So this is what I'm now going to just grab my snippet tool. Not that tool. Snip. And I'm going to take a screenshot. So there I can definitely see my equation and the 0 through 10 window that I asked for. And I'm going to save this as exam to review, although your guys's will actually be the exam, exercise 15A. So I saved it. There's part A done. Now, part B says find the velocity of the particle at t equal to 1.
Hmm?
So how do we do that?
You find the derivative of the function, and
Okay,
then you plug in 1.
perfect. All right, so part B, we need to find the derivative of s prime of t, which is our velocity of t. And we're looking for what happens at 1. Okay, so let's find the derivative first. What is the derivative of s of t going to be?
Uh,
Well, what's the derivative of 4?
well, 0.
And the 1/5 is going to come out in front. And so this will just be a chain rule.
Yeah.
So what's the derivative of sine?
Cosine. Well,
Okay. Cosine with 4 pi t inside,
yes.
because that's the outside. The 4 pi t is the inside. So what's the derivative of 4 pi t?
Times 1, 4 pi.
Okay. So if we clean this up, it looks like this. 4 pi over 5 cosine of 4 pi t. Of course, we don't really have to clean that up because all we're going to do now is substitute in 1. So we got 4 pi over 5 times cosine of 4 pi times 1. So really what we want to know is what is cosine of 4 pi? So we can go to Desmos real quick. Just type this in, cosine of 4 pi. And we know that that is now 1. So in the end, we got 4 pi over 5 times 1, which is
4 pi over 5.
label.
Centimeters per second.
Perfect. And that actually accomplishes part B and part C, because part C was all about what's the label.
Wait, so when you went to Desmos, you just put the cosine over pi, and then you got the one.
So yeah, I just went to Desmos and plugged in to figure out what that trig function was. So in part B, you would put 4 pi over 5. And then in part C, you're going to answer centimeters per second, which would be D.
In radians.
Yes, they want it as pi.
Okay.
Yeah. They do not want degrees on that. Okay. Any questions about number 15 and how that works? So there's a screenshot followed by a little bit of derivative work.
No, I'm good.
Yeah, I know. All right. Number 16. We're almost there. Number 16. So again, in this one, we want to find the equation of the tangent line to the curve y equals 3 ln of x all over x, and we got the point 1 comma 0.
Yes.
Okay. So we need to find the derivative first. How do we do that?
The quotient rule.
Quotient rule. So going back, it is the top function times the derivative of the bottom. Oh, no, sorry. It is the bottom function times the derivative of the top. OD high. I'll fill that back in. Minus the top function times the derivative of the bottom. All over our bottom squared. There we go. All right. So our bottom function is x.
Yes.
Our top function gives us what?
3 over x.
Minus our top function, 3
ln
x times derivative of our bottom.
1.
All over
X squared.
Okay. So just a little cleanup, even though I know we don't have to clean up. What's going to happen here between the x and the 3 over x?
They are gonna cancel out. It'll be
So that
3.
leaves us with 3 minus over here, 1 times all this will just be 3 ln of x all over x squared. So there's our derivative. Now, what are we going to do with this?
So now you're going to plug in 1 to get the slope.
All right. So we got f prime of 1. So it'd be 3 minus 3 times ln of 1 all over 1 squared. So what is ln of 1? And if you don't know, you go to Desmos and you
0.
just say ln 1, 1, 0. So this piece right here pretty much just goes away. And all we're left with is 3 over 1, which is 3. So there is our slope. All we do now, write our equation. y minus y1 equals m parenthesis x minus x1. And again, this is our x1 from the point. This is our y1 from the point. You've got your slope. So if we plug in, what do we have?
Y equals 0.
Y equals 0. Are you sure? How about y minus 0 equals 3 parenthesis x
Oh, wait, what am I doing?
minus 1. Yeah, I'm not sure what you were doing. Because when you plug in, that ain't going to be y equals 0. It'll be y equals what?
Yes, okay. 3x minus 3.
Good job.
Yeah.
And there you go. All right, 17 and 18. As I said earlier, we're going to go ahead and do these because they do have merit because they do give you practice on taking derivatives. But I've got better questions I want to ask than this. So on number 17, I'm going to change this one because I wanted you to actually find the equation of a line for this. So the slope is fine, but I'm going to modify this one right now, and I want you to find me the equation of the line. So we got this g of z equal to 3 over secant z plus tangent
So
z.
instead of just finding the slope, we go further and find the
Yeah.
equation. Okay.
Yeah, I want to go further and find the equation, but that's not the extension I talk about. That's not how I extended this problem. I just wanted to adjust this anyway to find the equation of the line.
Okay.
So the first thing we got to do, we got to figure out what is the derivative. And again, all that's going on here is a quotient rule.
Yes.
So you've got the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom function squared. So as we start moving through this, our bottom function is secant z plus tangent z. So I'm going to put that in parentheses. Oops, started to write tangent, although that wouldn't have been entirely incorrect because we can add in any order, but I'm going to keep the order. So secant z plus tangent z. You know what? I'm going to move this down to the next line too, because I'm going to run out of room. Okay. So secant z plus tangent z times the derivative of the top. What is the derivative of 3?
0.
So that's pretty much all going to go away.
Mhm.
Minus
3.
the top, which is 3, times the derivative of our bottom. So what's the derivative of secant z?
Secant z tangent z plus the derivative of tangent z, which is secant square z.
Okay. All of that is over
Secant z plus tangent z squared.
Okay. So just a little cleanup. We already know that this is all going to cancel. And this is going to leave us with a -3 secant z tangent z plus secant squared z all over secant z plus tangent z squared. Now, again, I know that we're gonna plug in, but I do like to just clean up. Do you see anything in common up here in this parenthesis that we could pull out?
Yes, you can take out a secant z and a tangent z.
I can't take out a tangent up here, but I can take out a secant. So we get -3 secant z. I'm going to pull that out, and that's going to leave us with tangent z plus secant
Okay. I see it.
z. And all this is over secant z plus tangent z squared. Do you notice anything else that can happen now? Because we pulled that secant out?
Yes.
What?
The top, the tangent z and the secant z, that one is gonna cancel out with one of the ones at the bottom.
Good. So this actually becomes a little bit nicer just with a couple things. Pull out that GCF and then do a quick cancellation. So our denominator is now secant z plus tangent z. And our numerator is just -3 secant z. Because this parenthesis cancels out one of the denominator ones. All right. So now we can start to write our equation.
Yes.
So we got this point up here. So what are we going to evaluate G prime at?
You
What did we
plug in the 0 to the
got it?
Yeah.
So we've got -3 secant of 0 all over secant of 0 plus tangent of 0. So if we don't know what secant of 0 is, let's just go into Desmos. And we can type in secant of 0. So secant of 0 is 1. And then we need tangent of 0. Type in tangent 0. Tangent 0 is 0. So if we come back to this, this is just -3 times 1, because that's what secant of 0 is. In the denominator, you have 1 plus 0. So what is our slope? Negative,
0.
no, -3.
Oh,
-3 times 1 is -3. 1 plus 0 is 1. -3 divided by 1 is
yeah.
-3. And now we can write our equation. So we got y minus y1 equals m parenthesis x minus x1. You know your x1 and y1 come from the point. So we got y minus 5 equals -3 parenthesis x minus 0. So what does y equal?
-3x plus 5.
Perfect. And last but not least, number 18. All you're going to do on this one is differentiate. But again, I offer up a different problem as well to this that I think is better suited. So we got arc cosine square root of x all over 7x. Let us differentiate this and be done. So again, quotient rule with a little bit of a chain rule as well. So we got the bottom function times the top derivative minus the top times the bottom function derivative all over g squared. Okay. So we got the bottom that is 7x, times what is the derivative of arc cosine? Because that's the outside and the square root is the
Yeah.
inside.
Would it
And it's-
be negative sine square root of x times 1/2 square root of x?
Okay, so we got to be careful. Remember, arc means inverse.
Oh,
The inverse of cosine, the derivative of that is not the inverse of
yeah.
sine.
Yeah, so it will be negative 1 over the square root of 1 minus x.
Yes,
Yeah.
because technically this is x to the 1/2, but that part is being squared in there. Okay, so that's the derivative of cosine inverse, but that's the outside arc
Yeah.
cosine. Now what's the derivative of the inside?
Times 1/2 square root of x.
And I'm going to keep this as x to the 1/2 for right now.
Okay.
Okay,
Yes.
so there's our first piece. A little bit of chain rule. Take the derivative of cosine inverse, which makes sure that wherever there's an x, you put x to the 1/2. And then take the derivative of the inside, which is x to the 1/2. That's where this guy came from. So we're going to subtract my top function, arc cosine square root of x. I'll just leave that the way it is, times the derivative of the bottom. What is the derivative of 7x?
7.
Okay. All of that will be over g squared.
7x squared. So
All
40.
right, so let's do some cleanup now. So first in here, this is, I'm going to put the negative up top with the 1. And this is all over, just like what you said, squaring a half, or in other words, a square root, just takes it away. So that'll be 1 minus x. Now over here, I'm going to kind of move this to my x place over here. So that's 7x all over 2x to the 1/2. What could I do with these two x's? This is why I didn't turn it back into a square root yet. What could I do with these two x's?
Subtract.
Subtract. So technically what we get, this will be minus 7 arc cosine square root of x all over. What is 7x squared real quick?
49x squared.
Okay.
These.
So you said we could subtract here. So what
Yeah.
you get is negative 7 square root of x on top, because 1 minus a half is a half.
Yes.
And so x to the half is just a square root. All of that is over 2 square roots of 1 minus x minus 7 arc cosine square root of x all over 49x squared. Is there anything else that you can see that we could possibly do up here? Anything that's in common on both?
Hmm. The the mm. Yeah, the sevens.
Pull out a 7, like a GCF. And again, that's why I offer up an alternative. This is a little crazy for a derivative on your exam. My alternative, definitely check it out. It's a little bit nicer. So that's negative
I'm up for the challenge.
arc cosine square root of x And all that is over 49x squared. So what's going to happen between the 7 and the 49? Just a little bit of reducing. So negative square root of x all over 2 square roots of 1 minus x minus arc cosine square root of x all over 7x squared. I kept this problem in because, again, we were dealing with derivatives of inverse trig. That's why I kept this one in.
Yeah.
And you had a little bit of chain rule.
Can you put
So,
the end part?
and again, I wouldn't expect you to get here. Like if you were able to just get the derivative done, that's great. But when you look at the alternative to number 18 that I put in, you'll see that this is the problem I give you as the alternative is much easier than this. I don't know what I was thinking when I put this question on there, but for the review, that's just it though. But we did some good practice of pulling out GCFs and reducing exponent values and things like that. And that is exam 2.
Got it.